Hi dear students, welcome to the next topic from the gravitation. So far we have learned about escape velocity, orbital velocity, and last sessions we have learned about the time period of the revolution of the satellites. And today now we are going to learn about a little bit of satellite parameters, and we'll do a couple of problems. Then we'll move to another important session which is called the geostationary satellites. So let's continue the topic, and the next heading is energy associated with the satellites. So energy of the satellites. So write on the heading energy of the satellite. Energy of the satellites. We know a different type of satellites which we are launching from the earth, and satellites are revolving in a particular orbit. So the satellites are above certain height from the earth surface. Okay, so you can assume earth is like a spherical structure or it's an elliptical structure, whatever. So above the earth is like a ball. So above the earth a satellite will be there, and the satellite is rotating at a certain speed, and it is above the earth surfaces. We know if you are taking anything above the earth surfaces or anything, if it is moving to a certain height, it is associated with potential energy. Energy in the sense there are two type of energies, right? Kinetic energy will be there, potential energy will be there. When a body should have a kinetic energy, if a body is moving, I can say the body have kinetic energy, simple words. So when the body will have a potential energy, if the body is lifted to some height, then it has potential energy. Now I have a questions to you. This energy of a satellite, which consists of only potential energy or only kinetic energy or both potential and kinetic energy? Answer is both potential and kinetic energy, because satellites are revolving around the earth, so it has motion, so kinetic energy is there. Second one, satellite is above the earth, it is not on the ground, it's above the surface of earth, so it is lifted to some height, so it also have potential energy. So satellite is associated with kinetic energy as well as potential energy. So the heading energy of the satellite. So energy of the satellite is equal to, I can say, I am saying like total energy is equal to kinetic energy of the satellite plus potential energy of the satellite. Okay, so we know we have a earth, this is the earth, and satellites which are rotating around the earth at a specific height, at a specific distance, and the satellites are revolving around the earth. Now, what is the energy associated with the satellite? Suppose the satellite is on the earth surface. From the center satellite, it is at a distance of r. Suppose it's not on the earth surface, from the center it is at some other distance. This distance I am giving as capital R. So at the earth surface, I am writing as total energy at the earth surface. Total energy at surface. What is the kinetic energy? Half into m into v square, kinetic energy. Here satellites are rotating. What is this rotating speed? Is called orbital velocity. If it is escaping from the attraction of earth, then it is known as escape velocity. So here it is orbiting, orbital velocity, plus the potential energy. We know the expression for potential energy always, but we know the orbital velocity is equal to root of gm by capital R if on the earth surface. If it is at some other distance, say small r, then it is at small r distance away. I can take it as at the surface, or I can take it as at any other distance other than the surface. If it is at surface, it is at a distance of r meter away, and if it is above the earth surface, at a distance of small r can be any values. So this we know. And what is the potential energy? U equal to minus gm divided by r. This also we have learned in the previous sessions. We are going to substitute these expressions over here. So total energy at the earth surface will be equal to half into m into v naught square. V naught is the orbital velocity. So V naught square, so Gm by R. V naught is root Gm by R. Square വരുമ്പോൾ the root will get cancelled. So Gm by R. And plus potential energy is minus Gm divided by R. So total energy at the earth surface is equal to how much? Gmm divided by R minus Gmm. This is a minus Gm by R is potential. Potential into mass is equal to potential energy. So how much is the total energy come? This is like minus 1. This is like 1 by 2. So answer is minus 1 by 2 G capital M small m divided by R. This is the total energy. Now how the questions will come for an entrance examination? Now if you look into this one, you can see three things. One is the potential energy, another one is kinetic energy, another one is total energy. What is the potential energy value? Minus Gmm divided by R. This is what we have written here. This is what we have written here. What is the kinetic energy equation? Half mv square. So this evaluation is Gmm divided by 2R. Now what you got for the total energy? Total energy is minus 1 by 2. So I can say minus Gmm divided by 2R. So one important questions will be there for the entrance examination. The question is, if potential energy is equal to minus x, if potential energy is minus x, then kinetic energy is equal to minus x means this quantity is x. So what is this will come? X by 2. And what is your total energy? Gmm by R is x. Minus Gmm by R is minus x. So minus Gmm by R is minus x minus x by 2. So this you have to remember. So now if you see potential energy, potential energy is negative, total energy is negative, kinetic energy is positive, total energy is half of potential energy, kinetic energy is half of potential energy in terms of magnitude. So total, if potential energy is minus x, kinetic energy is plus x by 2. I am explicitly writing a plus will be here, plus x by 2. Total energy is minus x by 2. Okay, this you have to remember at some point when we are doing certain numericals. These things will help you. For example, if in a objective questions, if they are given the potential energy of a satellite will be equal to minus 100 joule, minus 100 joule. What is the total energy? If this is minus 100 joule, then total energy will be equal to minus x is minus 100, right? Potential energy of a satellite, if it is given in the question, is equal to minus 100. Then what is the meaning of this one? Minus x is equal to minus 100. Then what is the total energy? Question will ask. I know minus x is minus 100. So minus 100 by 2 minus 50 joule is the total energy. So there are various flavors of the question will ask based on the concept. I will put another question. For example, the kinetic energy of a satellite which is revolving around the earth very closer to the earth surface. They will say like very closer to the earth surface means the distance from the earth surface can be neglected. So if it is very closer to the earth surface, then the total energy will be equal to 100 joule. Total energy, not total energy, kinetic energy is equal to 100 joule. Then what is the total energy? If kinetic energy is 100 joule means plus x by 2 is 100. Then what is total energy? Total energy is minus x by 2. So plus x by 2 is 100, then minus x by 2 is minus 100 joule. So answer is minus 100 joule. So while you see the questions, while you read the question, immediately you can pick the correct answers without any time lag. Within 5 seconds you can answer this question from this one. So additionally, what you have to remember means you have to remember these three formulas along with this x factor. X factor for your easy simplicity, I am telling, easy to calculate. So you remember this one, you remember this one. These two equations should be there on your formula book. Okay, so hope this is clear. So why the total energy? Here we see like the total energy of the system is negative. There is one concept, I don't know, you may hear in the small classes or very detailed we will study while we are going for the higher studies. total energy of a system is negative, then it is called a bounded system. A bounded system means if you want to take it from the boundary to another boundary, then you have to apply certain energy. For example, here you can see satellites are revolving around the earth or around the very closer to the, we can put it like an orbit will be here. So very closer to the earth surface or away from earth surfaces. So the satellite is bounded towards the earth surface with a force of centripetal force. Suppose if a satellite will be here, then there is a force called centripetal force. This is equal to gravitational force. Now centripetal force and gravitational force are equal, which means the earth is pulling the satellites towards its center. Why it's pulling? Otherwise it will escape it out and go, right? So earth, and it is pulling towards the center of the earth because of the centripetal force. Centripetal force is a force towards the center. Who is attracting the satellites towards the center? This guy. Who is this guy? Earth. So earth is attracting the satellites towards the center. This is the one point. So because of this attraction, because of the pull, always satellites will have a tendency to go out, but earth will not allow. It is always pushing towards the center. So because of the push towards the center, satellite is a bounded system. Bounded system means it cannot cross the boundary and simply don't go. Okay, if it is there, means it has to be there. So how I can take the satellites from here to here, from this orbit to this orbit? How I can take? I can give some extra energy so that the satellites can jump into the next boundary. But if it is here, or if it is here, or if it is in some other boundary, satellite is a bounded system. For a bounded system, in mathematics, for a boundary systems, the total energy is negative. It's a big theory, a big proof will be there, but as of now you understand, if you see total energy is negative, it is a bounded system. So I told you the definition of bounded system. This will not ask for the entrance examination, but your knowledge purpose I am telling, for a bounded system the total energy is negative. How? Why? What is called a bounded system? It is always binding towards each other. It cannot escape it out, in simple words. Hope you understood this one. Next, let's do a couple of questions and then we'll move to the next topic. Okay, fine. Let me clear this first. Hope you have written the things in the board. If not, yeah, as usual, post the video and complete the notes. Very important. All these areas are important. You will get a lot of questions from this area as well. Okay, fine. Okay, so let's move forward to the we'll do some couple of questions. I have some couple of questions with me, so let's do. So write down the question. I will write the questions for you. Two satellites A and B. You can write the questions along with me, so we will solve it together. Two satellites A and B are launched at an altitude r and 3r, at an altitude r and 3r from earth surface. From earth surface. If in question, if it is not specified from earth surface, you have to take it by default from the earth surface. Find the ratio of kinetic energy and potential energy. Find the ratio of kinetic energy and potential. Find the ratio of their kinetic energy, of their kinetic energies and potential energy. Kinetic energy ratio as well as for the potential energy ratio also we have to find out. Okay, so we'll do the question. Okay, so we have two satellites A and B are launched at an altitude of r and 3r from the earth surfaces. Find the ratio of their kinetic energy and potential energy. So first we will draw, we have two cases. First we will draw the two cases as explicitly. So we have the first earth will be there. Over the earth we have the first satellites. First satellite is at a height of r from here, but from the center it is at a distance of 2r. In the second case, we have a satellites and we have an earth. So from the earth, the satellites which are located at a distance of surface 3r. So from the center it is 4r, from the surface it is 3r. From the surface it is 3r, from the center it is 4r. Here also the same thing, it is r and 2r respectively. Next we have to find out the kinetic energy. I know the equations for the kinetic energy. So what is the expressions for the kinetic energy? What is the expression for the potential energy? Okay. So what is the equations for kinetic energy? Just before 1 minute we have seen. So kinetic energy of 1 equal to 1 by 2 into g into m divided by r. R is the distance from the center. Now how much is the distance from the center here? 2r. Question is given r, but we have taken 2r. Why? Because we are taking from the center. Very important. Do not take r. If you take r, if you solve, you will get one option. That option will be there as option A in your entrance paper. Okay, so 2r done. I'll go here. Kinetic energy 2 will be equal to what is 1 by 2 into gm, mass of earth and mass of satellites, divided by what is r value, divided by r. R is the distance from the center to the satellites, 4r. We have to find the ratio. So kinetic energy of 1 divided by kinetic energy of 2. These two ratios we have to find. So I will find 1 by 2 into gmm divided by 2r whole divided by 1 by 2 into gmm divided by 4r. Cancel, cancel. 4r will go to numerator. Answer is equal to 2. 2 is to 1 or 2 by 1. Answer is 2. I am writing potential energy. Potential energy is minus gmm by distance to the satellite from the center, again 2r, always distance from the center. U2 equal to minus gmm divided by 4r. What we need to do the second part? Kinetic energy ratios we have calculated, as well as we need the ratio of their potential energies. So u1 divided by u2, u1 divided by u2, minus and minus will get cancelled. This is also equal to, if you do u1 divided by minus gmm by r cancel, 4 is go to numerator, 4 by 2, answer you will get it as 2. So kinetic energy and potential energy, the kinetic energies ratios of and ratio of their kinetic energies given by K2, ratio of their potential energies, direct substitution. So kinetic energy ratio is 2, 2 by 1, 2 is to 1. Potential energy ratio is 2 by 1, 2 is to 1. Fine, perfect. So we'll go to the next question. I will clear the board, then I'll go to the next question. Fine. Pause the video as usual and write the notes very neatly. You can take your own time, but you have to understand the idea. That is the ultimate crux of studying for entrance examinations. Okay, fine, perfect. We'll go to the next question. Fine. The question is, I'll write the question. You can also write. A satellite has to launch it from a satellite has to launch it not from, at an altitude 2r from Earth's surface. 2r from Earth's surface. How much energy is required? How much energy required for launching the satellites? Much energy required for launching the satellites from the Earth's surface. How much energy is required for launching the satellites from the Earth's surface? A satellite has to be launched at an altitude of 2r from the Earth's surfaces. How much energy is required? for launching the satellites from the Earth's surface? The question is like that one. Okay. What is our intention? A satellite has to launch it at an altitude 2r from the Earth's surface. From the Earth's surface, I have to launch the satellites to a height of 2r from the Earth's surface. My final destination point is 2r distance away from the Earth's surface. So how much energy required for launching the satellites from the Earth's surface? How much energy I have to give? That's a question. So the idea will be the simple, the conservation of energy. So this kind of question you will normally face. How much energy? This kind of model, the word will be there definitely. How much energy? You see will be here. This is our Earth. Okay, and this is our orbit, we can assume, and the orbit is at a distance of 2r from the Earth surface. I need to put my satellites over here. I need to put the satellite. This is my Earth. So from the Earth center, it is at a distance of 3r meter away. It's 3r meter away. So what I have to do? Orbit. The satellites will be there on the orbit. Okay. Suppose when the satellite is very close to the Earth orbit, it has some 100 joule of energy. For example, I am assuming the total energy is 100 joule. Now, if I lift the satellites from here to here, I have to give some extra amount. That extra amount will add, suppose I have given that extra amount as 300 joule. So 300 joule of energy I given to the satellites. So what the satellites will do? Satellites already have 100 joule because it is at the Earth surface. It is rotating very close to the Earth surfaces, and which has kinetic energy as well as potential energy. Altogether total energy is 100 joule, for example. Then I am giving some energy, that is 300 joule if I am given. So 300 plus the existing 100. When satellites will be reaches will be here, it is 400 joule energy. Now the satellites acquire. Now the question is how much energy required, which means if I am giving you an hint saying like that, if it is at Earth's surface, it is 100 joule. If the satellite is at a distance 2r meter away from the Earth's surface, its energy is 400 joule. Hey, how much energy you have given? You will say 400 minus 100. You will say 300 joule is the extra energy I have given to the satellites to lift from Earth's surface to this point. You will say this one. How you will say? You are subtracting final energy minus this initial energy. So final energy is a higher value will be here. That's what we are subtracting. When we are going away from the Earth's surface, energies increases. Okay. So higher energy minus lower energy is the energy required. So I am writing the solution for this one. Energy needed or energy required. Energy needed is equal to the total energy. Total energy at what distance away from that center? At a distance of 3r minus total energy at a distance of r meter away. R meter away means this is the distance to the center is r meter. So r meter away 100 joule. 3r meter away 400 joule. Then 400 minus 100 is equal to 300 is the energy I have given. Remember 400 and 100 I have taken as an example to clear you the idea, but in our case it is different. So we'll see. So what is the energy? What is the total energy will be there? Kinetic energy plus potential energy. So what is the kinetic energy? I know the equation for kinetic energy. 1 by 2 into gmm divided by 3r kinetic energy plus potential energy is minus gmm divided by 3r. So total energy at 3r is over minus next factors, total energy at distance of r. 1 by 2 kinetic energy gmm divided by r plus minus gmm divided by r. This is what energy? Potential energy. This is what energy? Kinetic energy. This is what energy? Kinetic energy. This is what energy? Potential energy as well. So we have to take the difference. This is what we need to do will be here, so that our answers are available. So I have to take this space. So I am clearing. Hope you have drawn this one. I need to clear this area. I need some space over here. Okay, so let me simplify this one. Okay, so here if I am simplifying this one, how much is the left side? So is equal to, this is equal to 1 by 2. So how much will come? Minus GMM divided by 6R will come. If you solve these two, minus GMM by 6R minus of how much will come for this one? This will be minus GMM by, how much will come? 2R will come. Minus GMM by 2R. So now if I simplifying, I am correct, right? For the simplification, if I am taking 3RRs as LCM, then GMM by 1 by 2 minus 1. Okay, 1 minus 1, so 1 by 2, 1 by 6R, correct. So we'll simplify this one, minus GMM divided by 6R plus GMM divided by 2R. Okay, so let me take some things to outside. What I can take it as GMM divided by this 2R, I am take it outside. So what will come? 1 minus, or instead of doing like this one, it's quite simple, right? We will take 6RR as LCM. 6RR LCM means minus GMM plus 6R with 2R, 3RR. So 3 into GMM, 3 into GMM. Am I correct over here? Or if I done any mistakes over, will be here. No mistakes, right? Fine. So we got minus GMM by 6RR and plus GMM by 2RR. So we'll take the difference, total energy at a distance of 3R minus total energy at a distance of R. Simplifying this one, how much will get? 2 GMM by R in the numerator divided by 6RR. So which is equal to 2 by 6 is 3 by 2. So I can say GMM divided by, okay. So 3 minus 1 number 2, 2 by 6 instead of 3. So it is GMM by 3R is the extra energy in which I had to given to the satellite, so that satellites can be rising to the at a distance of 2R from the earth surfaces. Okay, we are going to see the next topic, and which is called geostationary satellites. So far we have seen about simply called satellites. Now we will see there are different type of satellites over the earth surfaces are located, and one category of the satellite which is called the geostationary satellites. So you can write down the heading called geostationary satellites. Geostationary satellite. The name has its own significance also as well. Okay, so there are GEO or GEOS, anything you can represent geostationary satellites. So let's have a look. There are three types of orbit, or three type of satellites are located in three different orbits. So three type of satellites in three different orbits. Okay, there are three different orbits are there, and each orbits will have a particular satellites are available. One is called LEO. LEO is called lower earth orbit. So lower earth orbit will consist of lower earth orbit satellites. Geostationary satellites, similarly lower earth orbits, and this is one category. This category of the satellites which are very closer to the earth, and it's not very far away, for example, and the first point is it's very closer to earth, and this kind of satellites are called lower earth orbit, and at a distance of 20,000 to 20,000 20,000 kilometers, 2000 to 20, approximately 2000 to 20,000 kilometer. Time required for revolutions to complete one revolution. Time required for revolution. Time required for revolution is 1.5 hours to 2 hours approximately. 1.5 hours to 2 hours is approximately. Okay. So this is a very closer to Earth, and it is at a distance of 200 to 2000. Sorry. 200 kilometer to 2000 kilometers, and time required to complete one revolution is 1.5 hours to 2 hours. 2 hours. This is just for your information only. There are no significant questions will not come. Next one is called MEO. What is MEO? This is lower Earth orbit. This is middle Earth orbit. Middle Earth orbit. Middle Earth orbit, this is not very closer but in a medium range. So it is at a distance of 2000 kilometers to 36,000 kilometers. 2000 kilometers to 36,000 means it is just above the what you can say lower Earth orbit. Just understand. This will also take the time required is approximately some 8 hours. Approximately 8 hours. It has some ranges. When the distance are increases, the time will also be changes. The third one is our main important thing, geostationary satellites, GEO in short. It's not middle Earth, it's not lower Earth, it's the third one. It's above this one. And here this is an altitude where it is located at an altitude of approximately 36,000 kilometers from Earth's surfaces, and the time required for revolution is 24 hours of time it should take. 24 hours of time. So 36,000 kilometers away this is located. This is less than 36,000 to 2,000 to 36, maximum 36. 36 will not reach. This is at a distance of 36 kilometers, and the time required will be is equal to 24 hours. Okay. 24 hours. So 24 hours is the time taken by the satellites to rotate the Earth. Okay. So hope this is clear. And but the name itself, if you look, will be if you look into the name, you can see it is geostationary. Stationary means what? It's not moving. The significance is like that. You know, Earth is rotating in 24 hours, right? Earth will be taking a rotation in 24 hours. Geostationary satellite is also rotating in 24 hours. So which means Earth is rotating. Geostationary satellites are rotating also with the same speed. So the significance, if you are looking from here to satellites, you are in Earth and you are rotating in every 24 hours, and satellite is also rotating in every 24 hours. 24 hours it is taking for one complete revolutions. So the relative velocity between the Earth and the satellites is 0. Why 0? Because both are, see, my both hands are moving same speed. So if I am looking from one hand to the next hand, if I am standing my one finger and looking to the next hand, I will feel that the next hand is also rest. Next hand is also rest because both are moving with the same speed. So I am here, I am looking for my next hand, both are moving with the same speed. I feel the geostationary satellite is at rest. That's why the word came will be called geo. The stationary means rest. Geo means with respect to Earth. With respect to Earth, it is at rest. That type of satellite is called geostationary satellites. Okay. So the geostationary satellites will have a specificity. It is covering or it is running over the equator belt, which means I will give you some details about this one. Suppose we have the Earth surface and we have something called equator position. So equator will be at the center. So the geostationary satellites are rotating along the equator belt. Along the equator belt means equator region is this one. So with respect to equator, it is rotating along the equator belt. So it is rotating along the equator belt. That's the point. So similar to geostationary satellites, another satellites will be there, but it is rotating at an angle. It is little bit of tilted. It is called GSS. GSS means geosynchronous satellites. Geosynchronous satellites. Geosynchronous satellites. So geostationary satellites are rotating in along the equator belt, along the equator position. Is the same geostationary satellites will also call it as a geosynchronous satellites, but the rotation will be inclined. Inclined means which is not rotating along the equator belt. So GEO and GSS are same, only the difference is the way in which they are rotating. So you can say GEO satellite, geostationary satellites rotating along equator belt, along equator belt. So similar to GOE, the same satellites is called GSS, geostationary satellites rotating at an inclinations. With an inclinations it is rotating. So geostationary satellites are along the equator belt. GSS are rotating at an inclination. With respect to certain inclinations it is rotating. Okay. Now for every satellites, if a satellites will be there, definitely the satellites will have a force of attraction. As I told, it is a bounded system. So it consists of the centripetal force, and which is equal to the gravitational force. So this already we know, Fc will be equal to Fg. Fc means centripetal force, mv square by the distance from here to the distance to the earth surface, mv square by r, and the distance between them is gm. This is the mass the satellites, as well the small m is the mass of the satellites, capital M is the mass of the earth, and at a distance of r. So if you simplify this one, we will get root of gm divided by r. Okay, this is the velocity of the satellite. This velocity is known as orbital velocity. Similarly, we have also learned about a time period. Time period is equal to distance by velocity. Distance is a circle, so the distance is a perimeter. 2 pi r, okay, speed 2 pi r divided by velocity is root gm by small r. Okay, so the balance I am writing will be here. So t will be equal to, how much will come? 2 pi divided by root gm into r raised to, here it is 1, here it is 1 by 2. So r power 3 by 2. So the important relation which is coming from here is t is proportional to r power 3 by 2, or t square is proportional to r cube. This is something related to Kepler's law. We are going to learn in the next sessions. Okay, so this is the time period of the satellites. So I have to write another equations. I know root gm equal to root of gr square. Am I correct? I know this equations, right? G is equal to gm by r square. So root gm equal to root gr square. If I am substituting over here, I'll get time period t is equal to 2 pi into root of another equation gr square into r power 3 by 2. These also you can remember. This is another expression. This already we have seen, right, in the time period of satellite. The same thing, the time period of satellites we already seen in the last session, and that is the same equations will be here for geostationary satellite, because geostationary is also a satellite. There in the previous lesson, the previous topic we have learned in the previous session, we have learned about generically a satellites. Now geostationary satellite means there is nothing special, only the position is very far away from the earth. Stationary indicate it is moving along with the same speed as that of earth. Its velocity, its time period equations, everything will be same as the normal satellite equations what we have learned so far. Okay, hope this information is clear to you as well. Okay, fine. we are going to start the next topic, Kepler's law, the last topic in this chapter, Kepler's law. Kepler's law, there are three laws are related with the Kepler's theory, and we have to know about various informations about the law and a little bit of what can say, a little bit of mathematics which is related to ellipse and which is related to circle. So such things we want to know. Okay, so let's start with this one, Kepler's law. Kepler's will have proposed three laws. We'll move with the first law of Kepler's, very important. There are frequently questions are coming from this area. Kepler's first law. Kepler's first law states that planets are revolving around the sun. Planets are revolving in an elliptical fashion around sun, comma, and sun will be the one of the focus. Sun will be the one of the focus. Statement is very clear, right? Planets are revolving in an elliptical fashion around the sun, grammatically around the sun, and the sun will be the one of the focus. So what this indicates? It's quite simple. With respect to an ellipse, we know semi-major axis, semi-minor axis. Very important. Little bit of mathematics are involved will be here. So please listen carefully. And this axis is called, it's called semi-major axis. And this y-axis, and this is called semi-minor axis. This is the origin 0, 0, and this coordinates will be a comma 0. And this coordinate is minus a comma 0. This is 0 comma b, and this is 0 comma minus b. Okay, so this is an ellipse structure, and a comma 0, minus a comma 0, 0 comma b, 0 comma, semi-major axis, semi-minor axis. What it states that the planets are rotating around the sun in an elliptical fashion, which means this is the planet, and this planet is rotating. This is an elliptical structure, and sun will be one of the focus around the sun. And the point is like the sun is located here. This is one point. This is the focus point. I can say one focus. I'll tell you what is the word meaning will be here. Indicate focus. So at the moment you can assume sun will be here around the sun. The planets are rotating in an elliptical fashion. Okay. Focus means, before going to focus, we want to know the equation of an ellipse. What is the equation of ellipse? Equation of ellipse. Ellipse and equation. Equation of ellipse is what? Tell me, what is the equation of ellipse? X square divided by a square plus y square divided by b square is equal to 1. X square divided by a square plus y square divided by b square is equal to 1. This is the equation of an ellipse. And this equation of an ellipse will also related with another important parameter. Okay, another important parameter means another important term which is related with this equation of ellipse. A is a semi-major axis distance, and B is the semi-minor axis distances, or we can say x distances, or we can say like a y distances. So there is a relations which is connecting between B and A will be there. What is the relations? The relation is B square is equal to A square into 1 minus E square. B square is equal to A square into 1 minus E square. This is also a relation from the mathematics. This is also from the mathematics. You don't want to by heart this one. First of all, I am telling you don't want to by heart, but you have to know. Okay, B square from your school's level of study, or from your 9th, 10th studies and all, you must know. So B square is A square into 1 minus E square. What is E? E is called, yes, you know, some of you know, I know, is called eccentricity. Eccentricity. But I want to know what is mean by eccentricity. Suppose tomorrow your very younger brother or younger sister is coming to you and ask me, hey, what do you mean by eccentricity? How you are explaining to eccentricity? I can explain to you eccentricity in a simple word. Eccentricity indicate the deviation from the circular nature to elliptical nature. You know, a circle is a perfect sphere kind of thing, but ellipse is a little bit stretched and lengthwise it is stretched, not a spherical structure. So eccentricity is the deviation. Eccentricity is the deviation from the circle. From the circle. I will give you one example. If I am taking a pure circle like this one, then I will say eccentricity is equal to 0. Eccentricity is 0 because with respect to an elliptical, this is not an elliptical, this is a pakka spherical, a circle, so eccentricity is 0. Now what I will do mean, I am just punching here. Now my structure will be a little bit of like this. Now I will say eccentricity is 0.7. Now what I'll do, I'm just punching it both sides. Now I am getting a perfect ellipse like this one. Now I'll say eccentricity is equal to 1. Now I'm sure you got what you mean by eccentricity. So more eccentricity means it is very, very closer to what kind of structure? Elliptical structure. Eccentricity is lesser means it is very, very closer to circular nature. That is the meaning of eccentricity. So what is the range of eccentricity? Eccentricity 0 greater than or equal to E greater than less than is 1. So eccentricity will lies between 0 to 1. In a simple way, 0 to 1. Okay, eccentricity will never equal to 0. It is slightly greater than 0, like 0.1, 0.2, something like that one. So 0 is an ideal case, 1 is also an ideal case, but normally the value of eccentricity is in between 0 and 1. Okay, so that we want to know. Now so this points are, hope it is clear to you. And the sun is located at one of the focus. Focus indicate. Now if you want to make the ellipse into circle, then you should have one point will be here, and this point is AE, 0. This is called focus. Here also you have minus AE, 0. Now if you take this point and if you draw the path, then it's look like a circle. Because the eccentricity is higher, you shrink the eccentricity, and you shrink the eccentricity means you are shrinking the ellipse and you are getting a perfect circle, and circle is passing through this line AE, 0 minus AE, 0, and this point is called the focus over here. So sun is at any one of the focus at AE, 0 or at minus AE, 0, anything you can take. Now for here, for the complete analysis of the Kepler's law, I am taking sun is at the focus, which means sun is at a coordinate of AE, 0. Here it is minus AE, 0. A is the full value, minus A is left side, plus A is right side. So planets are revolving around the sun in an elliptical fashion, and sun will be the one of the focus, which means sun is at a coordinates of AE, 0. Hope this is clear to you. Okay, I have couple of points. This is not finished at fully, but I have to clear this area. Okay, now the next point, all these points should be there on your notebook, whatever I am going to write. Now while you are looking to the diagram, this at this point satellites are very closer to earth. Satellite and the sun are very, not earth, satellites and the sun are very closer distance, and this point is called a perihelion. This point is called a perihelion. So perihelion is the shortest distance. Next heading you can give perihelion, or next point, perihelion is the shortest distance between sun and planet. That distance is called a perihelion. Important. Next one, as I told, the sun is rotating, sun is coming here, not the sun, the planet is coming here, and it will reach us here. And this is the farthest point. And this farthest point is called, opposite of perihelion is called aphelion. Aphelion. So I am writing the next word called aphelion. Aphelion is the, what is aphelion? Aphelion is the farthest distance. Aphelion is the farthest distance between who and who? Aphelion is the farthest distance between planet and sun. Planet and sun. And that is called aphelion. So perihelion understand, aphelion understand. Next, perihelion is the shortest distance, and this is given as R1. So perihelion is marking as R1. Aphelion is the farthest distance, it is marking as R2. For example, R2. So aphelion is R2. So perihelion and aphelion. Perihelion is the shortest distance, aphelion is the farthest distance. Now I want to write an equations for R1. What is R1? What is this distance? What is the total distance? A. So A minus, what is this distance? This coordinate is AE comma 0. So this distance is AE. The full distance is A. A minus AE is R1. A minus AE. So which is equal to A into 1 minus E. This is perihelion. And R2 is called aphelion. So this distance is A. This distance is AE. So R2 is A plus the shorter one, AE. A plus AE, which is equal to A into 1 plus E. So perihelion at a distance of, hope you understand, this distance is R1, the full distance is R2, and the distance from here to here is AE. Okay, AE I will mark it with a red color, and this distance is called AE. This distance is called AE. Okay. This distance is called AE. So R1 means total is A minus AE, you will get R1. If you want to get R2, R2 means the distance from this point to this point. So it is A plus AE. That's what we have written. So the distance, the perihelion is at a distance of R1 from the sun, and aphelion is at a distance. Aphelion is this point. Aphelion is at a distance of R2 from the sun. Okay, R2 from the sun. Everything we are calculating with respect to sun only. Okay, hope this is clear to you. We'll move to the second law. So we'll move to the next topic, and the Kepler's first law we have learned about detailedly. Now Kepler's second law and third law. So the next topic is Kepler's second law. Okay, so what is Kepler's second law? Kepler's second law states that the speed of the planet around the sun is different, which means, listen to the board first, then we'll write the definitions. Here we have our sun, here we have our perihelion, here we have our aphelion. So the planet which are moving around the sun in an elliptical fashion at a different speed, which means it's not a constant speed. So we'll write the definition. Planets moves around sun not at constant speed, which means it is moving with a different speed. Next point, what is the difference in that? What is the difference in speed? When it is at perihelion, when it is very closest to perihelion, when it is away from, when it is at aphelion, these two are the border points, right? Very closer point and very far away point. So we have a closer point and we have a far away point. So the speed at perihelion and speed at aphelion is different. So which means I can say speed at perihelion and aphelion are different. So in short, second law is try to say like that the planets which are rotating around the sun but with a different speed. In case for a perihelion, it is for perihelion and for aphelion the speeds are different, it's not constant. So now speeds are constant means where speed will be high comparable to perihelion and aphelion. Speed is higher at perihelion, so which means when the planet is closer to the sun, speed will be higher. Speed is lower in aphelion. Speed is higher in perihelion, speed is lower in aphelion. So this is what is the second law states that. Second law states that the planets are moving around the sun in an elliptical fashion, but each and every point its speed will be very less. When it is very closer to the sun, speed will be very high. When it is far away when it is a far away point, the planets are far away point, that point is called aphelion. When it is at aphelion, speed is very less. This is what the statements indicate. But so now I know, now I'll take like 3 regions. Suppose from here to here, the planet is traveled from this point to this point. So this much area it is covered. I'll take some other 2 points. So this is the area covered over will be here. From planets are traveling from A to A dash, some B to B dash, different points. So I'm taking some other points over here. Planets are traveled this area. Okay. So this area C to C dash. One more statement, what is second law states that one term is called aerial velocity. Aerial velocity is constant. I'll tell you what is called aerial velocity. Now I have taken 3 points over here in the diagram, right? Satellite is, suppose as satellites are started from A to A dash, from A dash to B, B to B dash, C to C dash, then it's going and reaches at A. So 3 sections I have marked. A to A dash. A to A dash, the satellites are traveled with an area of A1. With the area covered by the satellite. The area covered by the satellite is A1 and the time is T1. The area over here is A2 and the time is T2. The area over here is A3 and the time is T3. Okay. So satellites which are covered or which are traveled with different area and different time. But what is called aerial velocity? Aerial velocity, I am representing a term, the aerial velocity representing a term called VA. So aerial velocity VA is aerial velocity is constant, means dA by dt, difference of area by difference of time is constant. This is what is called the Kepler's second law, another definition. So what is dA by dt? dA by dt means A1 by T1 is equal to A2 by T2 is equal to A3 by T3 is constant. A1 by T1 equal to A2 by T2 equal to A3 by T3 is constant. So area, A1 is the area covered from A to A dash, taken time of T. So area is nothing but a distance parameter, right? Yeah. So this much area it is covered, this much maybe I can say area in the sense, for example, A to A dash. Maybe I am saying like the planets are traveled around the suns with covered an area of A by T. With an area of A and the time taken is T1. Similarly here it is A2, T2, A3, T3 and this area divided by time is called aerial velocity. Okay. So A1 by T1 equal to A2 by T2 is equal to A3 by T3. I told satellites will have a different velocity. So here it is V1, here it is V2 and here it is V3. So I can also say V1 not equal to V2 not equal to V3. V1 not equal to V2 not equal to V3. Important point. Do not consider like a V1 equal to A1 by T. No. This is not V1. V1 is a speed. A1 by T, see VA1 equal to A1 by T1. VA2 equal to A2 by T2, VA3 equal to A3 by T3. So both are different. This is the normal speed, and this is something called the aerial velocity. Both are different. So V1 is not A1 by T1. No, it's not like that. V1 is not A1 by T1. VA1 is A1 by T1, aerial velocity. This is the speed of the satellite. Speed of the satellites will be here. The satellites will go very fast, then slow, very slow. Then speed increases and shoot up. So it's a non-uniform speed. This is important. Area velocity of the satellite is constant. Okay, area by T1, aerial velocity of the satellite which is constant over will be there. Okay, so the point which is clear there. Now we will move to another one more definitions we have to write. Aerial velocity dA by dt is constant, and dA by dt, very important, dA by dt is equal to, we are writing an equations in terms of angular momentum, L divided by 2m. L divided by 2m. L divided by 2m is called the angular velocity. So aerial velocity is equal to L by 2m. So L by 2m is constant. Very important. We will use it in the many places of this one. Okay. Fine. So we are entering to a subtopic of this one. Speed of satellites at perihelion and aphelion. What is the value of speed? I told the satellites will be moving very fast at perihelion and very slow at aphelion. Okay, then what is the value of this one? How we will use some formula to derive that? Okay, so let me draw the diagram once again and we'll see. So this is an elliptical path where it is rotating, and this is our sun, and this is our perihelion, this is our aphelion, and the speed will be here is V1, speed here is V2, distance from sun to here is R1, distance from sun to here is R2. Okay, what is this coordinate? AE comma 0. What is this coordinate? A comma 0. What is this coordinate? Minus A comma 0. So what is from this one? What is called R1? R1 is what? A minus AE. Before we have written, right? So A into 1 minus E. What is R2? R2 is this distance. So this total, this is a coordinate of 0 comma 0. So A plus AE. A plus AE. So A into 1 plus E. Okay. Now what we are going to find out is speed. What is the value of E1? What is the value of 2? We know dA by dt is constant, and which is equal to L divided by 2m, angular momentum divided by mass of the satellites. So dA by dt L by 2m. I can say L divided by 2m at perihelion is equal to L divided by 2m at aphelion. This is a relation. This is a definition from Kepler's second law. Okay, you have to remember this expression. L by 2m at perihelion, L by 2m at aphelion. So L by 2m is constant everywhere. 2m is the mass of the satellite. So here same mass, same mass. So this will be get cancelled. So these two are get cancelled. So L1, so L at perihelion is equal to L at aphelion. What is angular momentum? Angular momentum in rotational motions we will study, and this angular momentum is R cross P, R cross P or RP, we can say R cross P. So R1, P1, R1, P2. So R1 into P1 means momentum, linear momentum into the R1 distance, R1 into linear momentum. So mass of the satellite is constant, speed is V1. So here it is R2, R2 into M into V2. Again M and M cancels. So V1 R1 equal to V2 R2. This is the relations connecting between the velocity of the satellites at perihelion and velocity of the satellites at aphelion. Very important. We will use this formula throughout to solve various numericals. Okay. So do not ignore those one. So it's really important to solve that. Suppose that if the value which are given in terms of eccentricity, you can as well substitute these stuffs will be here. So V1 into what is A1? A into 1 minus E is equal to V2 into A into 1 plus E. This also you can make use of it. This is in terms of eccentricity only we have written this formula. Okay, that is nothing else over there. Fine. So we'll keep there. So I have to clean this area. I have to write something else. So angular momentum is constant. Based on the angular momentum conservations, we have written this couple of formulas. Additionally, we have the energy conservations. Okay, so continuously write according to energy conservation. According to energy conservation. Energy conservation means energy is constant everywhere, right? From small class onwards we are learning. So the total energy here it is T1. Total energy at aphelion is T2. So TE1 equal to TE2. What all the energies will be there? It is rotating. Rotating means not on the earth surfaces. It's away from earth. Okay, so it has a potential energy as well as a kinetic energy. Satellites with the sun. So minus G, mass of the sun, mass of the satellites, divided by the distance from here. So with the respect to the here we are taking the distance is with, so these two are the energy associated. R1 plus half into m V1 square. V1 square is equal to the energy at aphelion. So what is the energy at aphelion? So this is equal to total energy at perihelion equal to total energy at aphelion. So what is the total energy? Minus G ms, mass of the sun. So you can write ms means mass of sun. Mass of sun. M is mass of satellite. Satellite mass. Okay, do not confuse these two things. Okay, so minus G ms m divided by R2 plus half into m V2 square. You can use, you can just remember or you can just understand this relation as well in terms of this one. Okay, you can simplify here also for R1. You know what is R1? R1 equal to A into, we have already written 1 minus E. So what is R2? R2 already we know, R2 equal to A into 1 plus E. This also you can substitute in the formula if eccentricity is given in the question, else you don't want to do this one. Okay, so perihelion and aphelions are, hope it is clear to you. Okay, and this R1 and R2 distances are also called perigee and apogee, but that doesn't matter or doesn't have any importance to this one. Okay, so hope it is clear. The R1 and R2 distances are called perigee and apogee. Perigee point and apogee points, or perihelion and aphelion, both are connected. Easy to remember, right? Perigee, apogee, or perihelion and aphelion. So okay, so we are moving to the third law, the Kepler's last law, and the last topic of this chapter, Kepler's third law. Kepler's third law generally will state that time square is proportional to r cube. But what is the meaning in terms of, if I want to solve some numericals, I have one ellipse, I have the next ellipse. So this is a semi-major and semi-minor axis. Sun will be located here. So at a distance of r1, at a distance of r2, time taken to complete this satellites for one revolution is t1. Time taken by these satellites to complete, which is in another orbit, is t2. Then what it states that t2 divided by t1 whole square equal to r2 divided by r1 the whole power 3 by 2. So this is important. So we have two satellites around the sun. One satellite will be taken a time t1 amount of time to complete one revolution. So t1 is the time period of first satellites at r1, and t2 is the time period of the second satellites at R2 at a distance of R2. So two satellites are in two different orbit. If that is the case, then generally time square is proportional to R cube. If you have two different satellites at two different points R1 and R2, so whose time periods are T1 and T2, and T1 is proportional to R1 cube, T2 is proportional to R2 cube. If you divide, you will get this equation. This is the most important equations. That is now 3 by 2, just like this. So if you take the square over here, it will become 3 by 2, right? Which means you can write the equations like this. T2 divided by T1 is equal to R2 divided by R1 whole power 3 by 2. Square will go to the right side, become root 3 by 2. You can as well write that equation. This is the Kepler's third law. Fine, perfect. We will do a couple of questions. Okay, so planets are revolving around the sun. Okay, planets are revolving around the sun at a different speed. Okay, mass of the planet is small letter m, mass of the sun is capital MS. Okay, so let's do a question. Let me have my questions on my hand, 1 second. So let's see. The question is, if the distance between Earth and Sun, is half of its present value, the number of days in a year would be, number of days in a year would be, So what is this questions indicate? Now initially we know Earth is a planet. First point, if you don't know, you must know Earth is a planet, right? Earth is a planet. For small classes we have learned this one. So now the situation is like this one. We have a sun's over is located over will be here, and we have our Earth will be here. Earth is a planet, Earth will be here, and sun will be there. The initial condition at a distance of d. Now what will happen? Now because of the certain situations, the distance between the sun and the planet is changed. Now this is Earth and this is sun, and the distance between them is d by 2. Here the time period is t1, here the time period is t2. If the distance between the Earth and sun is half of its present value, then the number of days. So we know the Kepler's third law, T2 divided by T1 whole square equal to R2 divided by R1 the whole cube. What is T2? T2 is a second case. So T2 I don't know. T1 is a first case. So first case means the distance between sun and the Earth. So what is the time period of Earth to rotate over the sun's? Okay, planet is rotating around the sun is 365 days, because the question is asking the number of days in a year. So with respect to year, here in a year will containing 365 days. So when 365 days will come, distance between the planet means the Earth and the sun is d. What happens when the distance between the sun and planet is d by 2? When it is at d by 2, how many days will be there in an year? That is the question. So the distance is d by 2 and the distance is d. Okay, so this is whole cube and this is whole square. So T2 divided by 365 is equal to 1 by 8 into root 4 into 2 root 2. So let's continue. So T2 equal to 365 divided by 2 root 2. If I am multiplying with the root 2 both the numerator and denominator, I will get 2 into root 2 into root 2. Okay, root 2 into root 2. So which means 365 365 divided by 4 into root 2. How much it will come? 365 divided by 4. 4, 36 and 9, 1, 10 2 times. 91.2 into root 2. How much will come? So root 2 is 1.4, right? Root 2 is 1.4. So 91 into root 2. So I'll simplify over here. So 91 into 1.4. 91 into 1 or 91.4, almost half. So approximately 136 days. You can solve it on the side of your notebook, but approximately it's 136 point something will come. But 136 days will be there in an year. So 365 days become now 136 days. Okay. Okay. We'll go to solve the last topic and the last question from this segment and from this chapter. Okay. Fine. Fine. The question is, we will write the question. Ratio of Earth's orbital angular momentum. Earth's orbital angular momentum about sun bracket with respect to sun. So Earth is a planet, will be here about the sun to its mass, which means angular momentum to mass is 4.4 into 10 raised to 15 meter square per second. The area enclosed by the Earth, the area enclosed by Earth's orbit is approximately dash meter square. Fine. We know dA by dt, which means simply I can say area difference divided by time is equal to L by 2m. But L by 2m is given, angular momentum to its mass ratio is given. So 4.4 into 10 power 15 L by m. This is nothing but L by m. But here we have 2m, so we have 2. Okay, so what is the time will be here? Area. Time is in terms of second, we have to say. So 365 days totally for an Earth with respect to the planet. 1 year is taken. So 365 into 24 hours into 60 minutes into 60 seconds. We are converting to seconds, divided by 2.2 into 10 power 15. Here also 15. If you solve this one, you will get the value of area. Area equal to 365 into 24 into 60 into 60. Answer is in meter square, right? SI unit. Into 2.2 into 10 power 15. You can solve this one, or you can just keep it like this. Okay. So I done with my chapter Gravitation. So the chapter is over. Chapter is completed. I hope you understand the things in which we have done. So please learn and understand the concepts in a perfect way. Okay. So do not by heart any formulas, any steps. It's not a very big chapter, not a very slow chapter, but it's an average size chapters. Now the chapter is finished, and understand and then learn the concept. Okay. So thanks for listening to all the videos of Gravitations. Hope you got something from me, and you got some information from me, but please utilize it and try to solve as much as questions from this chapter, so that you will get some confidence on this chapter. This is a very simple chapter, and simple chapter means a very simple lot of concepts will be there, but if you learn it thoroughly and if you practice it, definitely you can answer this one. There are not much very test kind of questions will not come, very straightforward, so you can easily solve it. Normally 2 questions will be there from gravitations, either 1 or 2. Okay, so it may contribute to some 8 marks or 4 marks, etc., but it's very important. Definitely 1 question minimum will be there in the question paper. Okay, so thanks for watching the video and have a nice day.